Hello and welcome to TWIST 2023. Welcome back. We're going to give everyone just a minute to log into the webinar and get situated. All right, welcome back to our final presentation of TWIST 2023. I have today Dr. Seth Veitzer. Seth is a senior research scientist at TechX. He's been with the company for nearly 20 years, specializing in ion source modeling, plasma surface interactions, and data visualization and analysis. He will be speaking today about modeling ion sources and techniques for speeding up VSim simulations. Welcome.
Thank you, Colleen. I'm glad to be here. I guess this is the last talk of the session, so I have only 54 slides, but some of this has already been covered, so I will defer to previous talks. To start off with, though, I'd like to acknowledge that Boulder is in the ancestral lands of the Arapaho, Cheyenne, and Ute nations, among others, and we recognize that this was their land. So here's an outline, two parts to my talk. First, I will talk about how you would go about creating an electrostatic model for an ion source, plasma chambers in VSim 12, and give some examples and walk through very quickly, maybe run through how that's done in Composer in the interface. And then I'm going to talk a little bit about techniques for speeding up your simulations of ion sources and what you can do to make them faster, because computational resources are always limited. First off, there are many different kinds of ion sources, and they're used for many different purposes. I'm going to focus on ion sources that have a plasma chamber to create the ions. Two examples of these would be capacitively coupled and inductively coupled, the difference being how the plasma is formed. Here's a diagram on the left of a capacitively coupled plasma ion source, and on the right, inductively coupled. You can see it's inductive because there are coils on the outside that are causing a magnetic field to heat the plasma up. On the right-hand side here, we have another inductively coupled plasma. This is used for implantation or maybe etching. And so there's no actual beam formed here, but it is an ion source, and those ions are put directly onto a substrate for etching or for implantation. In terms of modeling, I should say there are other kinds as well, but I'm going to focus only on ones that have a plasma chamber, and I'm going to focus on modeling the plasma chamber. So in terms of modeling, you can put it into a black box. There's three components to these types of ion sources. One is the plasma chamber. You can see my pointer, right? One is the plasma chamber. The second part of the ion source is the plasma meniscus and aperture, which Dan Faircloth just recently gave a talk explaining, focusing on that area. And then finally, beam extraction optics, which takes the beam and through some optics and massages the beam and passes it on to either a target or an accelerator or whatever. For this talk, I'm going to only concentrate on the plasma chamber and modeling of the plasma chamber. Okay, so I'm going to walk through now how you would create a model in VSim 12 of an ion source. And so I want to just jump out of here real quick and say, here is VSim 12, and I'm on the Setup tab. All of what I'm talking about right now will be on the Setup tab. And I'll go through how you would create this model. This is the model that I'm going to create. It's a Bernas type source, and my model is a two-dimensional model, and I'll go into that a little bit more. Okay. The first step is to create a computational grid. You do this by going into the basic settings, and you set, that's not the right thing, and you set your dimensionality. So this arrow should be pointing towards dimensionality. I'm going to do a two-dimensional model here. My coordinate system is going to be cylindrical, so this is RZ symmetric. So it's, yeah, 2D. And then we're going to do an electrostatic model here. So we choose all of those things in the basic settings. Then when we go to our grids, we'll find this dialog here that will allow us to choose the number of cells we want in each direction. We'll just choose some, for now, we'll just choose some large number of cells so we can look at the grid. Easy enough. Okay, so now we want to import geometry, and what we are going to import is a step file. The way that you do that is that you go in in the top level tree here, there's a geometries, and you select import geometries. That will give you another, you enter the name of the step file that you want to import, and then it will give you a dialog asking if you want to resize the grid. So in this figure here, you can see here's my grid, and then here's my geometry, and it's not the same scale. It's also not overlapping. So we'll get to that in a second. So you select yes, and we scale it, and now we have the same scale. The grid is still not aligned with the geometry, but here is the geometry that was imported as a step file here. And we'll need to make our grid overlap the geometry in the way that we want, but we're not going to do that quite yet. There's a better way to do that than just guessing at what the extents are of the geometry. Notice that this geometry has a lot of things that we don't want to model, right? We don't want to model these extraction optics. We don't want to model all of these things. And the step actually has, for every part of this device, there is a corresponding part in the step file. So I'll just mention that this hole right here is the aperture for the Bernas source. And so this is not a cylindrically symmetric ion source. It's actually inherently 3D. Most ion sources are inherently 3D because of the magnetic field requirements. However, when we're modeling the plasma chamber, we're going to make the approximation that is cylindrically symmetric. So we're going to essentially be modeling a cylindrical plasma chamber here that has close to the same dimensions, physical dimensions, and does not have an aperture. We are focusing here on building up the plasma, modeling the buildup of the plasma to try and get to a steady state for the plasma components. Okay, as I said, this geometry has many different parts. You can see in here that we really only want to focus on the plasma chamber. So that is in here in red. And then you can see the filament here that's going to create our electrons. And then there's some walls, and there's a cathode here, and then there's the repeller here, which is at the same voltage as the cathode. So there's all these parts here. So the first step is get rid of the parts you don't want to use. And so you can go through and you can go select each part in VSim and say, is this going to be part of my simulation? If not, you just remove it from the simulation. So eventually what we get down to is something that's a little bit more tractable. We only have maybe a dozen different pieces here. And I'm not showing the front plate here or the top plate here. Okay. Once you do that, and you've got the number of parts that you want to include in your simulation, you can then specify the X translation, X, Y, and Z translation, and the rotation of all of your geometry so that it intersects your grid in the way that you want it to do. And so this is a better way than moving your grid to the geometry, because this is not, the geometry's actually around the axis. This is a better way to do it because now I know that my grid is aligned with my cylindrical axis, and I've just moved my geometry and rotated it so that I have a good cross section here of my 3D geometry on my two-dimensional grid. Okay, that's a cool technique, and you can do all of this for each part. You can scale it, you can rotate them, you can translate them in 3D space. Okay, so now once we have this done, what we really have is, for our model, is an intersection of this 2D grid with the 3D geometry. And so this is shown here, and I've rotated the geometry here so that the grid does not intersect the aperture there. And so this is really, it's closed. For the modeling purposes, it's completely closed. All right. Okay, the next step is that we want to set voltages onto our geometries. And the way that you do this in VSim is first you add a conductor, a PEC, or perfectly electrical conductor. Is that right? Yeah, perfectly electrically conducting, or yeah, that's why we call it PEC. It's a lot easier. And you add that to your simulation. Right? So that's the first step. This is in the materials database view, which is another tab with a 3D view. So we were looking at the 3D view before, but you can look at the materials database and you can add these different materials to your simulation. So the first thing you need to do is add a conductor to your a PEC to your simulation. Then you select, for each part that you want in your geometry, you select. So here, this repeller here is selected as solid 110. And then you assign the material to be PEC. And do that for all of your materials. So now each piece of our geometry has a material assigned to it, namely a PEC. Then we can apply a boundary condition to those parts. The way that you do that is you go into field dynamics, you select field boundary conditions, and then you add a Dirichlet boundary condition. Once you do that, you'll get a little dialog down here. You can change the name of this to something that makes sense to you, because you're going to have every part's going to have its own boundary condition. Then you select for the boundary surface, that is a shape surface, meaning a piece of geometry. And then you'll have a list of all of your geometry parts, and you can assign that right there. So you do this for all of the different pieces, parts in your geometry, and then everything will be assigned. Oh, sorry, I forgot. And then you can assign the value, the voltage that you want here in the same dialog. So here I've set this to -1 times 10 to the 4 volts. It's always an MKS unless otherwise specified. So you do this for each part, and you also have to remember that if you have any boundaries on your mesh that are not intersected by metals, that you also need to set boundary conditions on the simulation boundaries as well. If you don't do that, VSim will tell you that you need to do that. So then you can solve the system, the Poisson solver. Okay, so now we've specified the voltages on all of our geometries according to how we want them. Now we need to add some particles. This is an ion source, so we need to add particles. In our simulations, we're going to start off with neutral particles and electrons, and we're going to incorporate the plasma chemistry in order to build up our ions and excited states. So the way that you specify particles, this is probably pretty basic for most people at this, listening to the talk. The basic settings, you have to include particles in the basic settings. And then we want to include reactions as our collision framework. Underneath particles, there's this estimated max electron density and max temperature. This is used to calculate the time step in case you don't give it an explicit time step, so that you're resolving the Debye length. So this will do a Debye length calculation for you, and then make sure that your time step is small enough. So then, now that we have particles, we can add kinetic particles, we can add fluids. So first we'll add kinetic electrons. You select kinetic particles, add particle species, add electrons. And so we have electrons in there now. We can also add charged particles. Usually we will add those as kinetic particles. You can either choose a built-in type, for instance, singly ionized argon, or you can do a custom type if you want to change some of your things. If you choose AR+, for instance, it will fill in the mass and the charge number and the ionization energy for you, or you can specify those on your own. You can also choose here whether you want your particles to be constant or variable weight. Ion sources, you probably want variable weight or managed weight. Managed weight is variable weight, but with splitters and combiners to keep your number of macroparticles small. Okay. So I think I just said all of this, but if you choose AR+, it fills in all the data for you. Use variable weight. Okay. Now, neutral species, we usually add as fluids to our simulation. So they're still particles, but they're represented as a fluid. The fluid does not flow, but it can be decremented. So to add that, you go to fluids, add a neutral fluid. You can rename the fluid. I've named it AR star here, because this is my excited neutral argon. You specify the temperature. I say a custom molecule. I'll get into that because I've reduced the mass here, but you can also choose existing molecules as well, and it will fill in all of these things for you. And you can set your gas density as well and where you want the gas to be. So you can set it put your neutral gas inside of your chamber, or you can put it in only part of your chamber, and you can set the density as well. All right, so now we've added our particles and our fluids. The next step is that we need to add particle boundary conditions. This is only for the kinetic particles. So if the particles go outside of your simulation domain, you'll get a seg fault and it'll crash. But what you really want is you want all of your geometry to absorb particles and do something with them, or just record that they've absorbed them, or just remove them from the simulation. And so to do that, under this species that you want, you can create I guess I didn't show this, but you can, for each piece of geometry, you can create an absorber, and you can tell it what the object is. So this object here is a part of geometry, and it's going to absorb the electrons. It's not going to do anything with them necessarily, but it'll absorb them. Similarly, for my argon, I have all of the geometry is going to absorb the argon when it impinges. And you also have to set absorbers on your simulation bounds, lower Z, and upper R, but not lower R, because that's the axis. And that should not, particles that hit the axis should be reflected back into your simulation, because this is cylindrical. Okay, so you have to go through and set up all of your particle absorbers here. Then the next step is we need a source of electrons. So here, I'm just going to do a simple source here. So I add a particle loader, and I'm going to load this loads from 0 to 1 second. So basically forever. And it loads every time step. Our time step here is around 10 to the minus, a few times 10 to the minus 11 seconds. So there's going to be a lot of particles here. And I specify which volume I would like to emit these particles on, or load these particles in. I can give them thermal velocities, et cetera, et cetera. You can change all of these however you like. You specify where you want them to be. And this will be our source of electrons that's going to go on and ionize the neutral gas. You can also set up secondary electron emitters in the same way here. You just choose a different emitter from your loader emitter. Did I miss that? Yeah, I missed that. Okay. You can choose secondary electrons here as well for all of your geometries. And this also, secondary electrons here can be either electron induced or ion induced. And we take into account that for ion induced electrons, the angle of incidence is important. Okay, next step is we're going to specify our plasma chemistry and our reactions. Daniel Main just talked about this, how to do this. So I'm just going to briefly go over it. We use quantumol DB to determine the relevant species and reactions. And then you can add all of your equations in here. So here's an equation. This is electron impacting on excited argon and ionizing it. And so you refer to the species that you've added, both fluids or kinetic particles here. And then you give it a 2-column data that comes from the quantumol database that has the cross sections for that. So do this for all of the reactions that you want to add to your simulation, and then you're done with that. How am I doing on time? Okay. Finally, all of these ion sources have an external magnetic field. Sometimes that's used to heat the plasma, but also to confine the electrons. The problem is that the electrons want to go off to the walls, and you want to keep them in the plasma so that they start to ionize the gas and keep the plasma sustained. So adding a magnetic field in VSim 12 is very easy. You just go to your fields, say add field, and say, I would like to add an external magnetic field. It gives you the option of what kind. You can choose magnetic field. You can rename the field to be whatever you like. And then you can either define it as a function of space for each component, or you can import an HDF5 file that has the magnetic field components in that file. That file needs to correspond exactly to the simulation grid that you've created. So if you change the number of cells, you need to change that file so that it's the same. VSim 12 provides an analyzer utility that you can run before you run your simulation that will create a file for you to use. And what this analyzer utility does is that it takes a CSV file that has position and maybe 2 or 3D position and the 3 components of magnetic field, and it interpolates them to your simulation grid and then writes that out into a format that can be read into VSim and can also be visualized in VSim. So this is pretty easy to use, but this is a new feature for VSim 12. All right, so once you've added all of your components for your simulation, then you'll end up with something that looks like this. So here's my simulation here. It's a two-dimensional simulation. I've imported my geometries, and they're all right here. Here's my grid. So here's my grid. I think if I click on it. Okay. And so I got my grid all set up here. We can see that there. Okay. My field dynamics, I've added an external magnetic field here. In my case, it's a constant. It's 10 Gauss. And then my field boundary conditions. So my boundary conditions I have for each piece of geometry here, I have a Dirichlet boundary condition. I also have boundary conditions on the simulation boundaries so that I can do a Poisson solve. I have electrons in here as kinetic particles with all of the appropriate boundary conditions. I have singly ionized argon in here with all of the appropriate boundary conditions as well. For fluids, I have excited argon and neutral argon in here. And then for my reactions, I have ionization, I have elastic collisions, I have backscatter collisions, excitation, de-excitation. And then I have some histories here so that allows me to have a log of things like the number of electrons. Okay, so now we are set up and we're ready to run. When you would go to run. Oh, it has to run that. So you go to run and you would run your simulation. Okay, so this simulation is going to be fast, but we have to run it for a long time to get to steady state. We're starting off with electrons and neutral gas. We want to end up with a plasma of argon and electrons. And so this takes a long time to get to steady state. So how can we speed up our simulations? So here are a few techniques that we can use that will make our VSim simulations faster. The first is the reduced dimensionality. I've already talked about this. But even though our sources are going to be inherently three-dimensional because of the location of the magnetic field and also asymmetries that are in the sources, we can approximate for the purpose of doing the buildup of, for modeling the buildup of the plasma, we can approximate this by an RZ symmetric simulation. Okay. Yeah. Okay. So here's an example on how this would speed it up. So the more cells you have, the slower it's going to be, or the more computational requirements you're going to have. So you want to reduce the number of cells. You could always throw more computers at it, and that works up to a certain point, but eventually you're going to have so few cells per computer that your scaling will decrease. So in a 3D Cartesian of 128 by 128 cells, you're at over 2 million cells. But if you made that 2D cylindrical as an approximation, you can reduce this down to 16,000 cells. So that's going to give you a big speed up right there. But you have to understand that this is only appropriate if you're looking at things like plasma buildup and not appropriate if you're looking at things like extraction. Because while you can make approximations there, the inherent 3D nature of it is going to get the physics wrong in some cases. Okay, the second is to reduce your plasma chemistry. Daniel just talked about this in the context of the wafer impact example. And it's all true, right? So you want to go through, you want to run your global model and see what doesn't change if you remove a species, for instance, right? Another thing that you can do, and QuantumAll does this, is pool your excited species. So there are many different excited states for neutrals and for ions. And often you can take those states and have one cross-section for all excited states or for many excited states. And that way you can reduce your number of reactions without reducing the fidelity of the physics. So I will skip over that. But here's just a little example for this case here, where or actually a different case, but similar, where I was looking at singly and doubly ionized argon here, and I had as a function of different excited states. And so from this is that if I don't include my triply excited argon here, then I get basically no difference in my steady state zero-dimensional model predictions for the densities. And so I could probably remove this from my simulations, remove the species and all of the reactions that are included with that species, and not change the results very much. So this is a very powerful way. All right. So in my simulations for these, I got about a 15% bump, not including by reducing the plasma chemistry. Okay. Energy conserving pick. So this is also Daniel Main's work. Energy in standard pick is momentum conserving. And so the particle charge interpolation to the mesh and the particle pushes are symmetric. All right, so there are no self fields. A particle does not feel a field from itself, and so momentum is conserved. In energy conserving pick, this is not the case, but it's done in a way where you're reducing the order of your splines when you're doing the interpolation back to the particles. And so because of this, it's called energy conserving. It's exactly conserving when the limit of dt goes to 0. But the advantage here is that this algorithm is stable at resolutions larger than the Debye length, up to maybe 10, I think maybe 10 or 20 Debye lengths. So this allows you to reduce your number of cells. It doesn't necessarily allow you to reduce your time step, because that might be dependent on other things, but it allows you to reduce the number of cells, which will save you time in computation. One of the downsides is that you have more noise generally in the particle distributions than you would have in a momentum conserving pick algorithm. So here's a quick example of that. This is a penning source. The plasma chamber is up at the top. The beam comes down, moves downwards. I'm just showing argon here, but there's also electrons in there. If you do momentum conserving pick, then and you're above, this is at about 4 times the Debye length of a resolution, then momentum conserving pick, you get grid heating pretty quick, and then it blows up. Whereas for energy conserving pick, it's stable and it reaches a steady state out here at maybe 8 to 10 microseconds or something like that. So this is a good technique, and I don't have a slide for it on how you do that in VSim 12, but I can just show you. Go here. If you go to basic settings, I believe it is the default setting. There's a particle to field deposition. Oh yeah, particle to field deposition allows you to choose energy conserving here. Yeah, so that is how you can do that in VSim if you want to, and that's on a okay. Another possible way to speed up your simulations is increasing the ion mobility. And that's just a fancy way of saying reducing the mass of your ions. And this works as long as the mass of the ions is, and the physics of the ions is fast compared to the physics of the electrons. And it's only going to work if you don't care about the actual trajectories of the ions. So if you're doing extraction, this is not going to work because the particles will not take the same trajectory as if they had the full mass. However, if you're looking at plasma buildup, then as long as it's slow compared to the electrons, then this is a good way to increase your performance. So here's some model results here. Here's my electron source. Here's my electrodes here, and then up at the top here is another electrode. This is not to scale. This is actually squished upwards. So here's the antenna, the filaments that are making the electrons in the real simulation, but I'm just approximating it by a slab that's continuously loading. And this is after 136 microseconds of simulation. I've run this out to about 340 microseconds. And this is a plot of the electron, approximate density for the electrons and the argon ions, and it's right on top of each other. And that's because the argon can move very quickly compared to if it had 730 times its actual mass is 730 times what you have in the simulation here. And so it can adjust a lot faster. Okay, so this is another way to do it, but you have to be careful. You don't want to do this in a case where the actual dynamics of the particles are important. Okay, and then finally, variable gridding and load balancing, and this is what was talked about this morning. Dan Murray talked about this yesterday, right? But and I guess Dan Faircloth, there's a lot of Dan's in talks. Dan Faircloth also talked about the variable gridding, but these are also ways that are important for ion source modeling, but probably more important when you're looking at extraction or you're looking at situations where you have particles only in one part of your simulation and not so much in another part of your simulation. When you're modeling plasma buildup, the particles are pretty well distributed evenly over your entire simulation. So this is not going to give you a lot of speed up necessarily. However, there are cases when it would. For instance, in some negative hydrogen ion sources that are used for neutron production, they produce negative hydrogen by impinging hydrogen onto a cesiated surface. And so in that case, you might want to have a finer resolution mesh near the surface so that you can resolve that physics a little bit better. So there are cases where it will help you, but primarily this is useful for the extraction, looking at the extraction. And again, variable gridding, as Dan Fairclough, is important when you're looking at the meniscus formation, where you have plasma and extraction. You want to have a variable grid near the plasma, and not so much when you're actually propagating the beam outwards. Okay, so here's some performance results for this model here that I've been talking about today. The full 3D model, we're looking at about 2.5 seconds per step on average, as opposed to about 150 milliseconds per step for the 2D model with the increased mobility and things like that. So approximately 16 times speed up by using these different techniques. Okay, and that's it. How did I do on time?
You did great. Thank you so very much. If people have questions, you can type in the bottom. There is a Q&A box, and we have one already. And it says, thank you for the presentation. Is it possible for us to produce a step-by-step PDF file to learn and create the same simulation? And I think that is certainly something. We are looking at building up a lot of our documentation and examples. So that is certainly an idea that we'll keep on our list.
Yep. And I think this presentation could go a long way towards that as well.
Yeah, it's pretty easy once you've got the PDF. Yeah, excellent. So thank you for the suggestion. Let's see. We'll just see if we have any other questions. We'll give another minute. I do want to say that all of these presentations, the videos will be on the TechX YouTube channel in about 1 to 2 weeks once we are finished editing everything and getting them up there. The other thing is, if you have not evaluated VSim in the last year, we are up to VSim 12.21. And so if you haven't go to our website at txcorp.com and request an evaluation, and we'll make sure we get you the latest version to play around with. And I think that may be it. I don't have any other questions, Seth. So on that note, I think we close out this event. So thank you everyone who has participated with us these last couple of days and this marathon of talks. It has been really enjoyable as always. Thank you, Seth, and thanks everyone else.
Thanks to the team for putting this together.
Sure.